for the solubility equilibria, we have a few calculations we can do. So solubility equilibria is referring to the KSP, which is our equilibrium expression for slightly soluble compounds. So the first thing we want to look at is writing our expressions, which hopefully you'd be familiar with because it follows the same rules that we talked about before for writing KEQ. These are actually simpler because we can ignore the reactant side because they're all solids. So our KSP is just going to be our ions in our product side raised to their coefficients. Alright, so if I only have copper ions and hydroxide ions, I have Cu2 plus times OH minus squared. Alright, for magnesium carbonate, I just have magnesium times the carbonate ion, both of them to the first power because their coefficients are 1. But if my coefficients are not 1, I'm going to have calcium to the third power in this one because I have 3 of them, phosphate squared because I have 2. Alright, and we're leaving out the reactants, remember, because they're all solids. So I don't have really a ratio. For KSP, I just have the products multiplied together, raised to their coefficients. So when we're trying to find the concentration then of some component of our solution, it really makes this very easy because our KSP is expressing concentrations of our products just multiplied together, raised to exponents. So in the case of the FeOH2, alright, I know this is going to break down into an iron 2 plus ion and 2 OH minus ions. This side is the solid. These ions are aqueous. So in terms of the equilibrium concentrations, all I care about are the products. Alright, now the question says what is the concentration of OH minus if 55 grams of my compound are put into solution, but it doesn't matter how many grams I put into solution. It's not all going to dissolve. That's the whole secret behind the slightly soluble compounds. I could put 100 grams in here and it's not going to change my answer because only some of this dissolves. And based on the KSP, very little of this is actually dissolving. So if I do my ice table and ignore the solid completely, we're going to start with 0 products. We're going to go plus S. Now using S instead of X is just the convention for solubility tables and to help remind you what the variable is you're solving for. Because the S actually represents the solubility of the compound. Alright, bringing down our coefficients like we normally would gives us S for the iron and 2S for the hydroxide. Now we're going to put this into a K expression. So S times 2S squared, nothing on the bottom because our solid doesn't go in here, and that's equal to the KSP value. Now we're given that value, 4.1 times 10 to the minus 15. Alright, so we can see the math here is fairly straightforward. We really just have 2 squared is 4, S squared times another S, so this is 4S cubed, equals our KSP. We're going to divide by 4 first, which really just gives us 1 times 10 to the minus 15, but I'll do the math. 1.025 times 10 to the minus 15. And then we do the cube root. So make sure on your calculator you know how to do cube roots, or even 4 or 5 for the root symbol. Alright, so if we do a cube root, at least on my calculator, I have this little symbol up here. Let's see if I can get this on here. I have this key right here that has the caret on it, and if you look above it, it has an x times the radical sign. So I'm going to do that. Okay, I'm going to have to put the number in first. So 3 to that, and then my answer. Alright, and that gives me 1 times 10 to the minus 5. Another option, if you're struggling to find the right key that will do this, so if I'm going to start with this, is to raise this value to the 1/3 power, and that will do the same thing. So if I do the little caret raised to 1/3, I get the same thing. So that is also an option. Alright, so this represents my S, or my solubility, so it's a concentration. But up here it asks me for the concentration of OH minus. So I'm going to go back to my table. OH minus is this, which is 2S. So my OH minus is going to be 2 times 10 to the minus 5. So multiplying my S times 2. So for these, it does not matter how many grams we're putting in there. This number is totally irrelevant to the calculation. All we need to know is the KSP, and we can solve this. So even if I dumped 100 grams, this number is not changing because I cannot dissolve anymore. Alright, let's look at some different ways to use the KSP value. Alright, in this case we're sort of working backwards. Instead of finding molarity, we need to find KSP. So we need to understand our concept. So what is the KSP value of AB3? The solubility, so that's S, is 0.00019. Alright, so first thing, write out your equation, because it's very easy to confuse yourself about what the ions breaking down would be. And knowing how these ions break down is crucial for using your KSP. So if I have an AB3, I have A to the 3 plus and 3B minus. Alright, that's really going this way as we break down. Alright, so in terms of KSP value then, I'm given S, and that's this number. If we filled in our table, if we do 0, 0 plus S plus 3S for our ion components, we can see where S is going to come in. But we want to put this into our KSP expression first so we know what we're solving for. So our KSP is going to be S times 3S cubed. Alright, so 3 cubed is not 9. I just want to point that out because usually that's what I get from students. 3 cubed is 9. That's not true. 3 cubed is 27. S cubed times another S is S to the 4th. Alright, and that's equal to our KSP. So when we plug in our S value to this, we can then solve for KSP. 27 times 0.00019 to the 4th power equals our KSP. So this is what we're going to put in. 0.00019 to the 4th power times 27. So I get 3.5 to the minus 14. So that's going to be my KSP. Alright, so we had to know how this was breaking down in order to get the right coefficients. the right exponents in our KSP in order to fill in our S value and get the right value. Alright, let's try another one. Finding KSP again. If we have x, y, 2, the concentration of y minus is 0.0097, what is KSP? So again, let's break down our compound. We're going to have x2 plus and 2y minus for how this breaks down. Alright, and we're given the y minus value. But let's do our ICE table and figure out what this would be. 2s, 2s. Alright, now it's telling us that y minus is 0.0097. We also know that 2s is equal to y minus. Alright, so 2s is equal to 0.0097, so we can calculate s. So we have 0.00485 for our S value. And then we can plug that into KSP. So our KSP would be S times 2S squared from our table. When we do our simplification, we get 4S to the cubed, 4S cubed. And now we're going to fill in S. So 4 times 0.00485 cubed. (4.56 to the minus 7). Alright, another way you can do it, since you know what y minus is you can also think of it this way. KSP is going to be concentration of X times concentration of Y minus squared, right? That would be our KSP expression. And we know Y minus, so 0.0097 squared. X, based on our stoichiometry, would have to be half of that. And we could then solve for KSP. 0.0097 squared times 0.00485 also gives us the same number, 4.56 times 10 to the minus 7. Alright, so when we're looking at comparing the amount of concentration we get from different ions from two different solutions, we could be tempted to look at KSP. We know the larger the KSP, the more soluble something is. The smaller the KSP, the less soluble. But in terms of actually calculating the solubility, we also have to pay attention to how many ions it breaks into. So in this case, which of these two would give us the greatest I minus? Now if we look at these two KSPs, we say, oh, CuI is more soluble, it has a larger KSP. But that's actually not the case if we look at it. This would give us an S squared equal to our KSP, because we have two ions, no coefficients. So we would have an S value of 1.14 times 10 to the minus 6. And if we look at the second one, we have a breakdown of 1 barium and 2 I minus. So this is going to be a 4s cubed compound. And you'll start seeing these over and over again. If it only has 2 ions, it's an s squared. If it has a 1 to 2, it's going to be a 4s cubed. A 1 to 3, like we saw previously, is a 27s to the 4th. So you can start seeing the same patterns over and over again. So if this is a 4s cubed, when we solve for s, we can see how this is going to be different from just doing the square root. Alright, so 9.2 times 10 to the minus 15 divided by 4, and then we do our cube root. So 1.3 to the minus 5. Alright, so we can already see that this s is larger than this one, so our BAI2 is actually more soluble because the s is our solubility. Now in terms of which one's going to give us the greatest amount of I minus, we need to look at what s represents. So in the first one, for our copper iodide, our s represents the I. So this is going to be the same concentration. For our second one, BAI2, our I minus is going to be a 2s. So we would need to multiply this by 2 in order to get our value. So 2.6 times 10 to the minus 5 is increasing the one that was already larger. So our barium iodide would have a larger I minus concentration than the copper. So we can't just look at KSP, we have to be able to solve for solubility and actually look at the breakdown, especially if the ions do not have the same number. If it breaks down into different numbers of ions. If they're the same number of ions, we can definitely just compare them straight. So let's look at this example. This would be like a test question. Which of the following would produce the most F minus ions in solution? Alright, so we have 4 different compounds. We have different KSP values. Since they break down into different numbers of ions, though, we can't just compare it based on KSP. But if we look at these, A and C have the same number of ions, and B and D would have the same number of ions. So we can compare between those two sets. So we're looking for the most F minus ions, so we're looking for the most soluble. So between A and C, we would be looking for the larger K value, which is going to be C. So we're going to cross out A because C is more soluble. Alright, then comparing B and D, because they have the same number of ions. Looking for the larger K value would be this one. So we're going to cross out B, because our D would be more soluble. So now we've eliminated half our choices. It's either C or D, because these two are the most soluble in comparison. Alright, so we have a very large difference here. So it looks like it's most likely going to be C, but let's solve for S. Alright, just for these last two. So this is going to be a 4s cubed. This one is going to be a 27s to the 4th. And if you're not clear on how to get that yet, write out the equation, do your ICE table, look at the coefficients. Alright, that'll help you. Alright, so if this one is a 4s cubed, then we can solve for s. 4.3 times 10 to the minus 9. We're going to divide by 4 and do the cube root. Oops. Alright, so our S is 0.00102. For C, okay, we're going to do the same thing for D. This one's a 27s to the 4th. So we're going to take our K value, 8.6 times minus 21, divide by 27, all right, and then do the 4th root. So that gives us 4.2 to the minus 6 for our S value. So we have a large difference here. Obviously C is a larger number for our S value. Because there was such a big difference here, we could kind of guess that, but solving for the S values really clarifies it. So this is going to give us more F minus. So even though this would be 2S for our F minus, we have 0.00204. This one would actually be 3S for our F minus, but even when we multiply this number by 3, it doesn't really help very much. Right, we'd get 1.26 times 10 to the minus 5. It's still several orders of magnitude too small. Alright, we're going to look at common ion effect on the next video.